Everyone, it's Miss Gogarty here. Just coming with the next part of section 2.6. Today we are going to be discussing the intermediate value theorem and trying to make sure that you have all of section 6 down. So last video we were discussing continuity and taking a look at what are the conditions for continuity within a graph. And so before we get rolling too much further, you want to make sure right now that you have the 2.6 notes sheet out with intermediate value theorem. You should be able to find that on your teacher's Canvas page. And yours might look just a tiny bit different from mine because I just copied in our 3 guidelines for figuring out continuity onto this page. But keep in mind, if you do not have a printer, it's okay. You can just make sure that you are copying all of this down into your notes, okay? So at the end of our last video, I had asked you specifically to try these first 4 problems on the intermediate value theorem notes page. So we're gonna do the first one together just to see how did you do and see how it's coming along. Remember that your teachers are posting the answer keys to these note sheets, so you want to make sure that you are checking your work against those answer keys so that we don't have any little minor mistakes in how to write things, okay? So let's dive in. All right, so the very first problem that I'm looking at here, I can definitely tell that we have points of discontinuity, okay? And easiest way, once again, is just to think of it as if I were to draw that graph, anywhere I'd have to pick up my pen or my pencil is giving me a point of discontinuity. So as I look at this, I can tell that I have a discontinuity at 1, I have a discontinuity at 2, and I have a discontinuity at 3, okay? Each of those input values creates either a hole or a gap. We could also have asymptotes in future problems that we have to take a look at a little bit closer. So the bigger thing here is, so what's the condition that failed for this function in that it's not continuous? Well, why? So let's take a look first at x equals 1. Now, I want to make sure that we remember here are the 3 conditions at which we would end up having discontinuity, okay, or not a continuous function. So if we take a look at x equals 1, well, at x equals 1, we have a hole, okay? So if we examine that a little bit closer, well, which continuity or which definition failed? And it's not that there isn't a limit. We definitely have a limit going on. I mean, and keep in mind, if we're walking from the left of 1 and we're walking from the right of 1, the values are, the outputs are definitely getting closer and closer to 4. So we have a limit. The problem is that at f of 1, we don't have a defined function. So actually, I'm going to keep that color. So where we have failure is that f of 1 is not defined. Sorry, my writing is a little messy at the moment. Okay, so now let's take a look at 2. All right, well, if I take a look now at x is 2, well, once again, I can be taking a look at this a little closer of, well, do we have a limit? I'm just going to ask myself, first of all, do we have a limit going on? So as we approach from the right, and sorry, from the left, got to get my directions down. As we approach x is 2 from the left and we approach x is 2 from the right, we definitely have a limit again, right? Our limit is 3. All right, well, let's go further. Is f of 2 defined? Well, yeah, f of 2 is defined right there. So f of 2 is defined. We have a limit. So what's the problem? Well, the limit as x approaches 2 does not equal f of 2. Okay, so let's look a little closer at that. What does that mean? Well, the limit at x is approaching 2 of f of x, this limit was 3, but f of 2 is defined at 2. These are not equal to each other. So the discontinuity is occurring because of the 3rd rule, okay? So let's move on. 3rd one, last one, okay? Now, if we're looking at the 3rd one, I'm going to get rid of these marks so they're not messing with us. okay? If we're looking at the third option, let's go through it. Is f of 3 defined? Well, f of 3 is defined as 0, so yes, does not pass the first one, it does pass, there's no problem there. Okay, let's look at the second one. Is the limit from the left the same as the limit from the right? And there's where my answer is no. The limit from the left is 0, the limit from the right is 1. So the problem here is that the limit as x approaches 3 does not exist. Okay? So as we're taking a look at these, I want you to be able to feel confident saying where is the discontinuity occurring, and then what is the reason? Like, why is the discontinuity occurring? What's the problem? All right. So you should definitely try the other 3 on your time and then check your answers with the answer key. Okay. But now for today, we're going to move on into something new. And our new is going to be the intermediate value theorem. Now, one thing that's extremely important about the intermediate value theorem before we even get going any further, okay, is that in order to be discussing intermediate value theorem, we have to be talking about a continuous function. If the function is not continuous, then we will not be able to make any conclusions about the things we're about to read, okay? Now, as with most math things, we have a very technical way of describing it, and you can all read this sentence right here of saying what is the intermediate value theorem, but the bigger point now is to just make sense of it. So what's happening here? Okay, so we're saying that we have a function that is continuous from A to B. So if I look at my first picture, I'm looking at this. From A to B, as my x's, I don't have a single hole, gap, vertical asymptote. There is no spot where we have a discontinuous function. Okay, then L, and which, by the way, L is just talking about some output. Okay, this is any output, but it's saying that the output is between f of A and f of B. So if I come down to this picture, notice L is in between f of A and f of B. Now, it does not have to be right in between them. We're not talking about a midpoint or anything like that. We're saying L is any value in between the output of f of A and f of B. So if this happens, we have a continuous function and L is in between A and B, then there has to exist a number, they called it C, in between A and B, so that f of C is L. So here we go. So we have some C here that's in between A and B, so that this point that we're looking at right here, f of C, is equal to L. Okay? Now, this is all well and good. I love the formal definitions, but let's just kind of look at this in a little bit of an easier light, okay? Let's talk real world problems, because there's a lot of examples that can really help make sense of this, okay? So let's just say in the morning, I'm just going to give you an example over here on the side. So at 9 a.m., it's, we'll go with 70 degrees, okay? And by 11 a.m., so 9 a.m. is 70 degrees, 11 a.m. it is 80 degrees. Well, what can you conclude, okay? What has to be occurring in between there? So, for example, if I come back to this picture, okay, I'm just making some room, okay? If I say that 8 here is 9, this A value is 9 a.m. and B is 11 a.m. So f of A, I'm going to call 70 degrees. And, okay, sorry, my iPad's wanting to do something interesting there. And then f of B is 80. Okay. Can you tell me that there has to be some time in between 9 a.m. and 11 a.m. where the temperature was between 70 and 80 degrees? Okay. Well, temperature is a continuous function, right? Like, it can't go from 70 to 80 degrees without at some point hitting all the temperature measures in between 70 and 80. Okay, there has to be a time. You could argue that it could be down to the split second or half of a second or whatever you want, but you can't go from 70 to 80 without passing all of the temperature values in between. So what the intermediate value theorem is saying is that there has to be some time in between 9 and 11 a.m. where there's going to be a temperature that's between 70 and 80 degrees. Okay, let's go to something else. Okay, let's go to driving. Let's say, as another example, you're going to say, like, right now, let's pretend we're driving. We're going on a mental field trip. So right now, the instantaneous rate of change of your car is 40 miles per hour. Okay. 5 minutes later, so now we're going into the future. 5 minutes later, the instantaneous rate of change is 60 miles per hour. So think of that like a cop sitting on the side of the road, and they have a speedometer of some sort. So you were 40 miles per hour, now you're at 60 miles per hour. Okay, can we conclude that at some point in between now and 5 minutes later, you had to have been going 58 miles per hour? Well, yeah, right? In order to get from 40 to 60, at some point, you had to cross 50, 58, okay? So I'm just gonna get rid of these again and just say, okay, once again, we have to have a continuity going. We're driving. So right now you're going 40 miles per hour, okay? And then later we're gonna be at 60 miles per hour, all right? And this is now, and this is plus 5 minutes. Because it's continuous, don't we know at some point we have to be going 58 miles per hour? But here's the better question. If we know that here is 40 miles per hour and here is 60, could you at some point between now and 5 minutes from now be going 30 miles per hour? Could that happen? I'm hoping you're saying, yeah, it could. It could happen. We don't know. Okay, could you be going 70 miles per hour somewhere in between here? Well, we could. We just don't know it. But if I said, would you know if you're going 50 miles per hour somewhere in between here? Well, yeah. So the problem is we don't know what's going on in between here, but we do know here's a starting point, here's an ending point. If I ask you for any value in between here, we can guarantee that. Meaning at some point on my drive, we have to be between 40 and 60 miles per hour. We have to. But at some point during the drive, I don't know if we're going to be outside of that 40 and 60 miles per hour. Okay? So let's make this a little bit more clear. Let's take a look at a problem. Okay? So I'm going to scroll down to the bottom, and it says, does the equation of f of x equals x to the third plus x plus 1 have a solution on the interval -1 to 1? So here we're going with our foreign language again, right? You have to know this vocabulary. What does a solution mean? In order for it to have a solution, what would we know? And by the way, before I get going on this is a no calculator type of problem. Okay, if you graph this on a calculator, then what was the point? Okay, so stay with me, no calculator, no Desmos. So back to has a solution. Well, this is the same thing as saying a 0 or an x-intercept. So we want to make sure that we understand the definitions, the terminology, the words that we're using, right? Okay, so we're saying that somewhere between -1 and 1. All right, well, let's start with, let's get what would happen on my graph. Okay, so I want to specifically know at -1 and at 1 what's happening. So first thing I need to do is find what is f of -1. So if I put -1 into my equation, -1 cubed plus -1 plus 1, okay. What's going to happen there? We're going to have -1 plus -1 plus 1. This comes out to be -1. Okay, so I have a point down here. What does f of 1 mean? Or what does it give us? And we end up with 3. Okay. If we know that this function is a cubic, okay, so I'm going to say we got to go back into our vault of knowledge. I'm going to start calling it that. Our vault of knowledge from Algebra 1, 2, and pre-calc. What do you remember about an x cubed? Okay, an x cubed is continuous. All right, that is the first thing that I want to make sure that we're getting out here. That an x cubed must be a continuous function. There's no place in this equation where we're going to have undefined values. There's no holes, there's no asymptotes, okay? So if we have a continuous function, then that means that there's no breaks from when we're here to here. All right, so I'm being asked, do we have a solution? Will we need to have an x-intercept to get from here to here? Now, the part that I want to make sure is clear to all of you, I have no clue if the graph is going to just do that. I have no clue what it looks like, and I am not going to graph it, so I don't even care. So I'm going to take that away, because the thing is, the graph could do something like this. I have no clue. The graph could do some weird thing like that. I have no clue. The graph could come down, then back up. I have no clue. Are you getting the theme here? I have no clue what is going on in between here, but I know that my graph has to start here and end here. So will you have to have a 0 if we start here and end here and it's continuous? Are we going to have to at some point have a 0? The answer is yes. We will have to have a 0 somewhere in order to connect this point to this point. But I don't know where it's going to be, okay? I can't even guarantee the range. So how do we say this? So we do know the answer will be yes, okay? And we know it because of the intermediate value theorem, okay? Because the intermediate value theorem is telling us that f of x, first of all, is continuous. We have to say that, because remember, intermediate value theorem does not work unless we have a continuous function. We know f of x is continuous on the interval -1 to 1. We actually know that this function is continuous everywhere, but we definitely know from -1 to 1 there are no points of discontinuity, okay? And f of -1 is going to be less than 0, which is less than f of 1. So here's where we're saying now the output of 0 is falling in between. This is the L value. L is falling in between a lower value and a higher value, okay? So because 0 is in between f of -1 and f of 1, there must be a value C such that f of C equals 0, okay? And this is how we are going to write up our answers. All right. Okay. So from here, we are going to try one more problem together, okay? And then you're going to just get some practice time. But in order to do this, we have to go to a new worksheet, okay? So I would like you to go to the 2.6 intermediate value theorem and continuity worksheet. So it should be the next thing that's listed in your Canvas, but basically take a second, pause the video, and go find the 2.6 continuity and IVT practice worksheet, okay? All right, I wanna take a look at these two multiple choice questions, and we're gonna go through them kind of quickly, so feel free to adjust the timing if you need it, okay? So the very first one that we're looking at, I'm just scrolling down, is the multiple choice. So the function f is continuous on the closed interval 0 to 2. Okay, I find it super helpful for myself if I make a graph. So I just want to get something that is showing me, in general, what is this looking like, or what's the possibility? So I know from 0 to 2, x is 0 to x is 2, we have a continuous function. Notice this again, that's really important, okay? And the values are given on this table. So I have a point at 0, 1 and at 2, 2. So let's see, 0, 1, 2, 2. This is all I know so far. Now, what they're asking here is what could k be so that f of x equals a half is going to have two solutions? Well, first thing I want to do is, what does f of x equals a half look like? I got to do this. F of x equals a half is like a horizontal line coming across at a half. So in order for this to happen, think about it, like I know that the graph is continuous from 0, 1 to 2, 2, but I cannot determine that it just goes like this. Okay, I cannot make that distinction. I don't know that information. So I'm getting rid of that. Heck, how do I know that it doesn't go up like this? I don't, okay? But now this question is saying we want to have two solutions. That means two intersections. So what has to happen is that this graph has to go down somehow, cross this green line, or intersect the 1/2 twice. Well, which of these y values would allow that to happen? Well, if 1, 0, if I had a point here, well, yeah, then the graph would come down and then go back up. Okay, that could happen. Hold on, I want to clear up a little bit here really fast. Okay, change the color. So if y is a half, then my graph would come down and go back up. Well, that would give me two intersections. There's my answer. If it's only a 1/2, we have a problem. Okay, oops, I erased too much there. I'm gonna go back. Okay, if the y value is only a 1/2, the graph itself would only come down and then go back up. We'd only intersect once. That would be bad. Okay, if I kept going further, if the 1, 1 would be a point here, 1, 1 would be bad because now it's doing something like that. We're not even close to the 1/2, and otherwise these values are too high. So we're actually using kind of the concept of intermediate value theorem, that we needed two solutions. All we can determine from 0, 1 to 2, 2 is the start and end, but I don't know what's going on in between. Okay, so last question for this video. All right, once again, I'm going to make a table or a graph for myself to just help out a little bit. Okay, so I am told, I'll look at that nice word again, continuous function from -3 to 6. Okay, so -3, 1, 2, 3, 4, 5, 6. So f of -3 is -1. So that point right there. And then I also have 6, 3. So it'll be about there. Let's say 1, 2, 3. Okay, so the graph starts here at -3, -1, ends at 6, 3, because we read our graph from left to right. We know it's continuous. Okay, so which of these can we conclude? Okay, do we know for sure that we have a point at 0, 0? So if we started graphing from this point, from the first point to the second point, do we know that 0, 0 is going to be on there? No way. I have no clue what is happening. I mean, why can't my graph go like that? It could, right? Why couldn't my graph go like this? It could. Heck, craziness. Why can't my graph look like that? It could. So I do not know 0, 0. Okay. B, here's the good news. You have not learned that notation yet. If you haven't learned that notation yet, that's not going to be the answer that the calc teachers give you. Okay. We'll learn what that means coming up, but for right now, I can assure you that is not the answer. All right. So problem solving skills at our best right there. So let's go to C. So in between -1 and 3, so f of x has to be between -1 and 3 for all values -3 to 6. Okay, what this is telling us right now is it's saying that the range must be -1 to 3. Well, everyone, I just gave you how many different graphs that I don't know what has to be happening in this middle here. I don't know. There's so many different options of connecting this first point to the second point. I can't guarantee that the range has to be between -1 and 3. Okay, so let's go to D. F of C equals 1 for at least one C in between -3 and 6. Okay, so now they're saying C. Okay, what does this mean? That there has to be some input where the output equals 1. Does that have to happen to get from the first point to the second point? No matter how we go about connecting these, whatever option I come up with, will I be guaranteed that at some point I have to have a value that is going to cross this green line at 1? Yes, there's my answer. It has to happen. Okay. Now, at the same time, f of c equals 0 for at least one point. You got to look really close at this last one because it's a little tricky. So at the end of the day, my Zoom just decided to crash a little bit there, but it was right at the end anyway. So at the end of that last problem, we couldn't make a conclusion about E. So hopefully it's going to make sense to all of you that D has to be the answer. Okay, so that's going to conclude our intermediate value theorem. Let us know if you're having any trouble. And other than that, I hope you all have a great day. Thanks. Bye.